if you have only a memory of size n, okay, if you have n bits of memory, how many states are possible? How many configurations? Only 2 to the n. That means that after 2 to the n time, you will necessarily encounter the same memory as before. And then your computation will cycle. Okay? So you will never be able to do anything interesting. I mean, that's, you will be very limited. So you need unbounded things to tell something interesting. Okay? So that's why, for instance, we usually consider that we can always add memory to our computers. Okay? That's an important thing. I mean, you never program thinking that you will have a limited memory. You always program thinking that you can have all the time as much memory as you want. Okay? That's very important, because else you will not be able to do as much as you want. So basically you have this infinite tape, and on this tape, there are at the beginning there is the input that is written with some sharp, an infinite number of sharp to the left, an infinite number of sharp to the right, okay? And you have 0 and 1s, which is the input, okay? And you have a head here, a read-write head, but at each step, read the symbols on the tape, at the place it is, okay? Look at its current state. It has a finite number of steps, states. You can think it as the instruction of your program, okay? And given what he reads on the tape, its current state, it will change its state to a new one, okay? Write something on the tape, and move the head to the right, to the left, or just stay in place. Okay? Some kind of very stupid thing, okay? But you can see it. I mean, you can really see this systems working. Okay, so that's what is nice. And an important thing is that at some point you may decide to stop. Okay, if you read that and you're in that state, then you stop. Okay, so at that point we read what's written on the tape and we say that it's the output of the machine. Okay. So basically we have here a system that allows to do some computation. Okay? And the Alan Turing thesis, which is also known as Church thesis, because we are two competing models at that time, is that everything that this thing can compute is everything that every other model can compute. Okay? We cannot compute anything else but what's computed by this model. Okay? So that's a pretty huge assertion. But it turns out that this model, where they were able to prove that it's equivalent to Gödel 1, it was equivalent to lambda calculus Church 1, and to anything. And ever since, we never found another model that could do more. Okay, with finite resources, finite unbounded resources. Okay, so that's basically a very convenient one because it's fairly simple, and we can see what's going on, and we can understand, and we can also realize it for real. For instance, if we look at here, some crazy people did it for real in Lego. So it's, if you search for an argument to buy some brainstorm Lego, it's Mindstorm Lego. It's the moment or never. So here you see that there is the tape. So when the brick is to the left, it's 0. When the brick is to the right, it's 1. Okay. So you have some kind of sensors that look at where the brick is, and it's related to a computer that tells you what's the next transition to do given the position. So you see that it tests, it reads and moves away and go back and forth. So so it's a pretty concrete model, but at the same time it's a pretty theoretical one. So what's the problem with this model is that it's quite inefficient because you can move only by one position to the left, by one position to the right, so the access to the memory is terribly slow. And, it's something awful, but anyway, it's a fairly nice model. So the nice thing is that, you know, this model was in 36, okay, and the first computer was, I thought it was the ENIAC in 46, but it turns out that there was another German one in 41 that was bombed in 43. So now it's disappeared, but it was reconstructed later on. But anyway, the fact is that the Turing machine was, some kind of conceptual model of computation that allowed to build computers. Okay, and the main step afterwards was the work of von Neumann, who was working on the atomic bomb, also, and who came up with the architectures that we know now. That means that the memory is no more a tape, but a real memory where you can access to any position with cost 1. Okay, and that was a huge step, a huge improvement over a Turing machine. Okay, but it does not give anything more from the theoretical point of view. Okay, so you have these architectures, and pretty much it stayed the same for until now. Okay, so what's so specific about this model? What's interesting is that it allows to think about computation in a very nice way. And what you obtain very easily from this model is that basically you can find a universal Turing machine. What do I mean by that? It's a Turing machine for which it takes on its tape at the beginning the code of another Turing machine. Okay, so you can find an encoding of a Turing machine in 0 and 1s. Okay, such that if you write it on the tape here and you follow it by an input, okay, then this universal Turing machine will execute exactly this Turing machine, will emulate this Turing machine on this input. Okay, so that's basically fairly easy. I can explain it to you. It's basically here what you do is that you just write all the entries of the transition table. Okay, so what you write here is basically that if you read this letter and you're in that state, then you go in that state, you write this letter, and you move in this way. Okay, so you see that it's a kind of quintuple of integers. Okay, so you can write that here. Okay, and you have the input here. And what does the universal machine do? Is that at any point it writes on the tape the current state of the machine, of this machine here. Okay, read the input here, read the state there. Okay, and then look for this state and these numbers in the table, and then do everything that's written in the transition table. Okay, so what's important here is that you see that all these operations are local. You can do that by just going back and forth between this tape here and this one. So you just go back and forth here, and you can solve it for them. So universal Turing machine exists. Okay, so that's nice because this means that we can build computers that you build just one computer and you will be able to execute any program. Okay, so that's also an important result that allows to design computers. Okay, you have one computer that allows to execute anyone. Okay, so that's for instance a compiler. You can imagine that it's a compiler. Okay, so this may seem something like a trivial result and not very interesting, but it turns out that it has huge consequences. First is that universal computation is of very modest complexity. I mean, there is just one machine that can do everything. Okay, so you don't need a huge number of states, you don't need sophisticated systems to do everything that is possible to do. Okay? And second, when I put here the code of the Turing machine and the input next to each other, basically there is no huge difference between both of them. Okay, you could put the input within the code of the Turing machine and it will not change anything. Okay, and basically what turns out is that this result here, the existence of a universal Turing machine, shows that data is equivalent to program. Okay, and this may seem like a trivial idea, but it has huge consequences. For instance, if you imagine the DNA is exactly that. You have data and at the same time the computation. You're built from the DNA, but they read the